Hello, everyone. My name is Vijay. I'm a staff data engineer at TRM Labs data platform team. And today, I'm going to be talking to you about our journey of building a real-time blockchain intelligence system with Beam and Kafka. So if you are looking into building one, I hope our journey offers you some insights that you can take with you. First off, what is TRM Labs? So we are a blockchain intelligence solutions provider that we help organizations detect, investigate, and respond to financial crime. We have a global customer base that includes government agencies, crypto businesses, financial institutions. Here's a quick overview of what I'll be talking about today. I'll begin by talking why we need real-time intelligence at TRM Labs. Then I'll talk a bit about our journey of building one. We'll also explore some stream processing architectures along the way, and I'll also discuss why and how we chose Apache Beam with Dataflow as our stream processing engine. And then I'll also try to cover some practical recommendations that we use, some design principles that we follow, and techniques that has helped us scale our data platform, our stream data platform efficiently. To begin with, I think this was also touched by one of our keynote speakers. It's very important to understand and think about why you want to build a real-time system. For TRM, To answer the why for TRM, let's take a moment and step into the shoes of our customers. Imagine that you are a law enforcement agent and you're closely tracking the flow of funds as a scammer moves them through a haze of blockchain wallets, trying to obscure their trail, and then finally they try to sort of cash that out at a exchange, but you manage to catch them. As you can imagine, this is a really high stakes scenario. There are real people's livelihoods that are at stake. And that's the business reason behind which TRM needed a real-time blockchain intelligence system so that we could catch such activities and help our customers make some real-world impact. Now that we know why we needed a real-time intelligence system, let's talk about how we built one. First, I want to talk about the architecture, right? So this is usually the first step that you'd think about when you're starting out building a real-time system. There are several different architectures that you can look at, and each has its own characteristics or trade-offs. In our case, we evaluated Lambda architecture and Kappa architecture. Lambda architecture it's a dual-layered processing system. So it has a batch layer and a stream layer. Batch layers are usually something that would handle your daily large volumes of data. Think of them as your ETL or ELT pipelines that run hourly or daily. And then you have the stream layer that sort of acts on events as they are generated and provides low latency insights. This architecture is usually it's more fault tolerant because of the dual-natured data processing, but at the same time there is more complexity and overall cost to it. In contrast, Kappa architecture is just single-layered processing that handles that basically handles everything for you. It's obviously easier to think about, but there is some trade-off there in terms of how it handles your heavy batch-style workloads. We chose the Lambda architecture. The reason being we wanted that fault tolerance, and we deal with huge amounts of data, petabytes of blockchain activity data on a daily basis, and then that meant the batch pipeline is more efficient at handling that kind of data, especially when we are looking at backfills, because we can optimize those scenarios with operators like copy to move a large amount of data to our serving layer. So once we have our architecture chosen, the next step was choosing the right stream processing engine. This was a considered decision that involved like finding the right balance across multiple dimensions such as performance, scalability, maintenance overhead, cost, and also like the compatibility with our general overall infrastructure. We also factored in other things like the skill set of our team members, and then what are our longer-term goals with respect to the platform. One of that is running TRM Labs on multiple cloud providers. And then we began like shortlisting various options. So Beam with Dataflow was one of that, Spark streaming, and then we had Flink and others as well. And now before I sort of deep dive into the evaluation itself, I want to sort of preface this by saying that these ratings that you see on the screen are not universal. This is what we had. This is based on like TRM's needs, is existing infrastructure and preferences. My goal here is not to give you a sort of not to rate these engines, but rather give you a framework that you can use to make such decisions. So why did we choose Beam plus Dataflow? Well, several reasons for that. So we have, because of its managed nature and features like auto-scaling and built-in optimization, Beam with Dataflow is performant, scalable, but at the same time requires very little maintenance. That was a very crucial factor for us, given the size of our team. It's a smaller company. And additionally, we operate a very wide footprint of GCP. We're basically using a GCP product, so there's a good level of integration with Dataflow, with things like cloud monitoring, PQ. And one aspect of using a managed service like Dataflow is that it can cost you a bit of premium if you're not, as opposed to running your open source. However, when you factor in things like engineering time that you save because of basically the maintained nature of the managed nature of the Dataflow, and then also some of the new factors like Dataflow Prime, it becomes a very valuable option, and it compares well across costs as well. And then finally, one of the crucial aspects of Beam is its portability. So you can take basically the same Beam code and then run that on different engines. As I mentioned earlier, running the platform on multiple cloud providers was a key decision factor for us, and therefore, like, Beam made a lot of sense. So now that we had our stream processing architecture, and then we also had our stream processing engine. Let's talk a bit about like some of the design principles that we follow at TRM Labs to make sure that our system is scalable and can adapt to changing needs. So number one is decouple your compute streams from the data persistence streams. This design principle has paid off in several important ways for us. One of them is reduced blast radius and specialized pipelines. So by isolating the compute and write stages into separate data flow pipelines, we basically reduce the blast radius. If something goes wrong with the downstream data store, only one of those pipelines is impacted, not the entire system, and we can always fall back to the other data store if you're running a blue-green deployment like us. And then backfills are pretty hard if you're running a stream system. With this architecture, you could choose a targeted backfill for a very specific data store. So That's helpful. And then most importantly, future proofing, right? So you could use the same computational results that you store as part of the intermediate result set. It could be in a Kafka or a PubSub, and then add another write stage that would just consume from the same computation that you've already computed. You don't have to repeat. You don't have to repeat the entire computation there. Design principle 2, try and avoid streaming joins. I don't say that because it's not possible, but because they are complicated. They introduce edge cases and operational complexity, and it's very difficult to reason about them at scale and debug. FYI, we did not start that way. In our V1, we had a lot of stream joins, and that's possible due to Apache Beam's rich set of features like windowing, triggers, and watermarks. But there were some issues, as I mentioned. It increases the overall complexity. Debugging is hard. But most importantly, the data quality. It's difficult to achieve 100% data quality when you're using stream joins. So that's why we moved to something called a unified stream approach. The way we define unified stream approach is we treat streaming as a first-class citizen in our data processing systems, where the systems that are responsible for generating the stream events generate the events in its entirety. That might mean that the events are a little bit larger, so you might have to sort of play around with the message sizes in Kafka and those sort of things. But the benefit of that is the downstream processing pipelines can just take that whole event and process that and then output that, so you don't have to do the stream joins. Again, this is not always possible, but when it is, we try to do that. And what that means is our pipelines are simpler to reason about, and the data quality is the same as a batch pipeline. Design principle number 3 is we take a layered approach for our write stages. So write stages are super critical, and the reason for that is no matter how fast you compute your data pipelines, the computational pipelines, if they don't persist into the data store that you're serving your customers with, it's basically there's no point to it. So we spend a lot of time in optimizing that. As I mentioned, we take a layered approach. So the layer 1 for that, we treat the layer 1 as the data flow pipeline itself that's writing to the data store. So we do several things there. One of them is JDBC batching, and then we also use a temporal buffer. Within that temporal buffer, we do deduplication of data before actually writing that to the data store. So data store doesn't have to do that as often, and that sort of helps take some of the load away from the database. Layer 2 is the network layer, and it's something that gets often overlooked. However, it's super important if you really want to optimize the latency of your end-to-end system. One of the things that we do is we make sure that our data flow pipelines and the data stores or databases are co-located in the same network zone. So that helps you sort of improve your latencies. And then next is we pay super close attention to timeouts, which are socket timeouts, session timeouts. There is a very interesting issue on Apache Beam's repository, issue number 19069, that has a bit of detail that I also sort of help contribute to, is how socket timeouts can sort of catch you off guard and mess with your pipelines. So if you're interested, you can take a look at that. And then the layer 3 is the database layer itself. So you have the so at TRM we use Postgres. So I'm going to talk a little bit of Postgres things here, but even if they are not directly directly related to whatever database you are using to, you could probably take the same concepts and then apply that to your use case. So first is always use a connection pool. I can't tell you how many times I've seen that, and we've had that personal experience that the data flow pipeline opens hundreds of connections because you have different 5 nodes in there, and then just opens so many connections. And if you have hundreds of pipelines, it's just gonna kill your database with like way too many write connections. So be careful about that. We use Hikari CP, but you can use any others as well. Second is table design. We are very deliberate about what kind of table design we use. Things like indexing and partitioning are usually based depending on the access pattern of those tables, read and write. We also go a step further when we need like extra boost with things like unlogged tables. If you're familiar with Postgres, those are tables that avoid write-ahead logs, so you get a boost in performance, write performance, but that comes at a cost of like crash recovery. And that might be an overall acceptable scenario for you, especially if you're operating a Lambda architecture like us. So that's something to consider. And the third is the write conflict handling strategy. I think, so at TRM we use based on the data that we're dealing with. So if it's something like a log event that's immutable in nature, we generally have on conflict do nothing strategy. But if it's something more stateful, there's usually on conflict do update strategy that we use. And then this is something that I'm particularly excited about talking is that I earlier mentioned that Beam does have portability across runners, and we did know that when we chose Beam. However, what stood out really well to us was how well it performed when we put that to test. So at TRM Labs, as I mentioned, we are a heavy GCP user. So our initial set of pipelines or system was on Beam plus Dataflow on GCP, but we soon had to migrate that to AWS as well. So we were able to take our same Apache Beam code that's written in Java SDKs and then run it on Flink that's deployed on Kubernetes in AWS, and it went super smooth. Only real code changes that we had to make were around deployment pipelines and observability monitoring, those sort of things. Apart from that, the core Beam code sort of worked like basically without any code changes. So yeah, if what I spoke to you, or what I spoke about today is interesting to you, we are hiring. Check us out at trmlabs.com, and that's it. Thank you all.